Here, the same problem, find the extreme values of function x double x plus 3y subject to the constraint x squared plus y squared equal 4. We can proceed the way we proceed with the triangle problem. We can parameterize the boundary. In this problem, it's a perfect case to do that because circle has a very beautiful, symmetric, and nice parameterization. Here it is. If I take the parameterization for my circle, canonical way to parameterize the circle, and if I restrict my function onto this parameterization, it will be the case which will help us to solve this problem. Look at this. If I now take my gt function, which is my f on this specific parameterization, it will be my function on the boundary. Alone, nothing else. So here's my function, double x plus 3y, but now cos t sine t, over this interval, and we have to minimize and maximize this function. It's a first year problem. Minimize the function over the domain. That's something we experienced 3 times with you when we did the triangle boundary, because on triangle boundary we use 3 different parameterizations. It is even better here because we use this beautiful parameterization for the circle. For the boundaries of triangle, it's boring because it's a line parameterization. Here, it's shiny. Okay, so how do we do it in the first year? We compute the derivative. Here it is. Derivative of my function. We equate that derivative to 0. We come up with a solution. These are the stationary points. So this solution, it's a trigonometric equation. You can just take, say, 6, and then it's a 4 sine on the other side, divide everything by cos. You will end up with the equation tangent t equal 3 on 2, which we know how to solve. Within this interval, this has 2 solutions. It's the first solution. That's the second solution. These are it's an opposed solutions. They sit on the different ends of the diameter. These 2 solutions, here they are. This is a T1 point, or this is T1 angle, I should say. This is a T2 angle, plus half of the revolution. 2 of these angles, they give you a solution to this equation. These are the 2 points you have to study. So before you proceed, you have to find the cos and sine at these values. It's another elementary task, which you know even from the school, how to find the other trigonometric functions if you know the value of one of the trigonometric function. In this case, we know the value of tangent, 3 and 2, how to come up with the values of the sine and cos, which is associated with that. It's an elementary task. It's not a unique solution. There will be 2 values, one of them with 2 values, of course, one of them here, one of them here. So for the T1, you got sine and cos like this. I'm skipping some trigonometric evaluations because it's a part of the elementary school. High, but still elementary school, how to do that. For second value, these are the values of sine and cos. And we're done. Now I have to compare the values of my g in these 2 points, which if you reflect back in terms of f, you have to compare. So here's my comparison, g of t1, which is f of double cos t1 3 sine t1, and that is the value at this point of my function, and that's the value of my function at the second point. This is the max, this is the mean. Would you agree with that? Basing on your first year experience, would you agree with this? There's something hinting probably you shouldn't, right? Yes, no? No. Why no? So why no? Maybe yes? Well, the first year method, on the top of checking the values of your function everywhere the derivative is 0, it insists as well on checking the value of the function at the endpoints of the interval, which I didn't do. So the answer is no, it's not a complete solution. My interval, my g function of one variable, first year stuff, nothing serious. We found those 2 points where derivative is 0, but we didn't check negative pi. Well, in this case, it's actually 1 point. It's not 2 points. Because even though in terms of t it's 2 points, back in the parameterization language, it's 1 point here, -1, right? Under this parameterization, both negative pi and pi, they all end up in the same point, this one, -1, 0. So I still need to check the value of my g at negative pi and pi, which is f of -1, 0. I still need to check this line. I mean, I need to make this check before my solution will be complete. Well, it's an easy check, isn't it? F -1, 1, -1, 0, I'm sorry. My function is, here's the function. -1, 0 across this function gives you -2 value. So my function at this point is -2, which doesn't affect any of these two values because root 13 larger than 2. And that's why still root 13 is a max and negative root 13 is a mean. But this line must be here, otherwise your claim for max and mean is not without a flaw.